Nope. Okay. So, this is our first example. Friendships. Moose is friends with Meg, Ginger, and Betty. Jughead is friends with Ginger and Betty. Archie is friends with Veronica. And Reggie is friends with Betty.
What are these names?
These are actually from no, it's not from Riverdale. It's from a comic book.
Well, his name Moose.
I had a homeboy named Moose. He would really look. Man, you say he looked like Moose. He remind you of
My uncle's nickname was Moose.
I know what June Bug. I don't know what June is.
Jughead.
Yeah, that's Jughead.
Oh, dang, Trey. Heard of him before. Oh, yeah, I know what Jug is.
Okay, so we need to draw a picture where the edges are the friendships that they have and your vertices represent your people. So, how many vertices do I need to create this picture?
5. No. That's 4.
Oh, how many people?
Your vertices have to represent your people.
8.
There are 8. Okay. You're going to need one for Moose, Meg, Ginger, Betty. You then need Jughead, Archie, Veronica, and Reggie. So you need a total of 8 vertices. So again, go ahead and put down your 8 vertices and label them with names wherever you want to put them.
I know somebody named Reggie. He cut hair.
Right.
Reggie cuts hair.
All right.
Okay.
You probably know Reggie.
The Reggie, the one here.
Boy, no. Wait,
What's your problem? There's pencils in that container over there.
Man, they took all your pencils again.
Why don't put them out anymore?
Would you give me extra credit if I bought you some more?
I have plenty, thanks.
What about tissue?
I have plenty, thanks.
What you need? What about glue?
I have plenty, thanks.
Answer the time.
Boy.
Yes. What? That's my out with this.
Okay. So now, the edges that we draw between our vertices have to represent the friendships that they have. So, our first line says, Moose is friends with Meg, Ginger, and Betty. So, Moose should have an edge that connects him to Meg, to Ginger,
And Betty.
and to Betty. Then it says, Jughead is friends with Ginger and Betty. So we need to connect Jughead with Ginger and Jughead with Betty. Archie is friends with Veronica. And Reggie is friends with Betty. So you should be able to use this graph to answer questions like this. Who has the most friends?
Moose.
Moose and Betty. Okay. How many friendships does Moose have? 3. His degree is a 3. He has 3 friendships. There's 3 lines coming out of his vertice.
Betty has 3.
Betty also has 3. Who has the least amount of friends?
Reggie.
Veronica.
Reggie.
Veronica, Reggie,
And Meg.
Archie.
Archie,
Meg.
and Meg. They only have 1 friend apiece. What else did you notice from this graph?
Ginger has 2.
Ginger has 2.
It's disconnected.
Jughead has 2. It's disconnected.
Oh yeah,
Okay.
I forgot about that.
So Veronica and Archie are only friends with each other. They have no other friends, according to this.
You like that sometimes.
Right on God.
better like that to keep it going with you.
Hey, listen, it's not about how many friends you have, it's the quality of your friends.
Yeah.
I can count my true friends on one hand, and I'm okay with that.
Right. And I count my true friends on no hand. I don't got no friends.
That's how I am. If either I call you family or you ain't nothing, yo.
Okay.
Like that.
We can also represent sports using graph theory. So, we're talking hockey games, okay? Your edges are going to represent the games that have been played. Note that the day of the week is not important. We don't care that you played on Monday, Wednesday, Friday, Thursday, okay? Your vertices are your teams. How many vertices do I need in this picture?
1, 2, 3, 4, 5, 6, 10.
We need 6. We need 1 for Pittsburgh.
Yeah.
We need 1 for DC. We need 1 for New York. We need 1 for Philly. We need 1 for Chicago.
You hear me?
And we need 1 for St. Louis. So, what's my first line I should draw?
What is Pittsburgh and DC?
St. Louis. You said what?
Pittsburgh and DC.
Pittsburgh and DC. Okay.
But you're gonna have to do that twice, so you're gonna have to.
It's fine. Okay. So, Rames just said I've got to do that twice because on Tuesday they play again. So we've got a multiple edge there. Okay. Cross them off as you go. New York plays Philadelphia. Chicago plays St. Louis. New York plays St. Louis. Philly and Chicago. Pittsburgh and St. Louis. New York and DC. Philly and Chicago again. Philly and DC. Chicago and Pittsburgh. St. Louis and New York.
There's 2 at St. Louis and New York?
Yes.
That is tricky.
Right.
Yo, that John crazy, you hear me?
I should be able to give you this graph, and you should be able to answer questions like, how many games did Chicago play?
4.
4. There's
They
4
all
lines
played 4.
coming off of Chicago. They're all 4. Each one of these has a degree of 4, so each team has played a total of 4 games. All right. Examples 3 and 4 kind of go together. So, what's happening here is we have a neighborhood watch that wants to be able to patrol each block the community has after they've had a bunch of burglaries. So, our roads are going to be our edges, and our vertices are going to be the intersections where you change direction. So, what that means is each one of these should have a dot. Every one of them. Wherever you would change direction to go up a street, you should have a dot. Okay. So, you start at any dot you want, and you're patrolling the streets. So, we go down the street. You go down this street. down this street, okay? As you patrol the neighborhood, you've got to go down each street to make sure that it's safe. So your graph model should look like this. Oops, I missed one.
Shootout.
Them is patrolling it.
Right.
Man down, man down.
Cocaine.
I was gonna let cocaine was.
Who said something about cocaine?
Okay. Watch what I do with this next one. Okay. Still the same idea. Each intersection is a vertice. I need to not draw this on the map. I'm going to draw this beside the map. So I've got 1, 2 here, and then we've got 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. 2, 3, 4. Okay. Watch what I do here. We're going to talk about why this one looks different than the other one.
Oh, because he has to go on both sides of the road.
Okay. Notice all the ones on the inside. I drew multiple edges. Okay. And Marcus has already stole my thunder. It's because as a mailman, you don't get out and walk anymore. Okay. They drive up one side of the street, drop off mail. Well, guess what? They got to turn around and come back the other side of the street because there's houses on the other side too. Okay. So when you have to worry about going up and down the street instead of just up the street and looking both ways, you have to represent that in your graph by a multiple edge. Does that make sense? And we've got one more. And this section's over.
For real?
For real.
You know what's good.
Feel me, dog?
I feel you.
It's new, man.
Yes.
Oh,
It is
for real?
officially March.
Hey,
What the world?
we're gonna go back too fast.
Word.
And you have 64 days left until graduation. Oh, wait, no. You got 64 plus 180.
Damn. Oh, dang.
Because you'll still be here next year.
Oh, my God.
I'm not.
Doesn't it suck to be a junior?
Barely. I graduate this year.
You good now?
Senior.
I like this.
Hold on, I'm not done.
This is my best year of high school.
Best year of
That
high
sucks.
school?
Yeah, for now to next year.
Till next year.
I graduate this year.
Where
How come you don't go up and down the edge of the outside streets?
Because your houses are along the block here.
Oh.
So you only need to go up one side of the edges.
Wow.
All right. Mr. Ames.
I'm good.
So we can also do this with school zones. Okay. So this is Winston-Salem, Forsyth County. Okay. Each school zone is going to be a vertice. So we've got a dot at North Forsyth, a dot at Reagan, West Forsyth, Mount Tabor, Reynolds, Parkland, Atkins, East Forsyth, Glen down here in the corner, and Carver up top. Okay.
Run away.
The edges in this one is going to represent the different school zones that they border. So if you take a look at this picture, North Forsyth borders which school zones?
Reagan, Mount Tabor, and Carver.
Okay, they touch Reagan, Mount Tabor, and Carver. What school zones does Carver touch? Well, we already did North Forsyth. What else does it touch? Mount Tabor. I heard East Forsyth, Atkins,
And Reynolds.
and Reynolds.
Yeah,
Even though it's just a little section here, it does touch Reynolds. East Forsyth,
Oh, Bliss.
Glen,
Atkins.
and Atkins. Okay. What about Glen?
Where's Glenn at?
Parkland. Atkins. East Forsyth.
Parkland,
Atkins.
Atkins, and we already have one to East Forsyth. Okay. What does Parkland touch?
Reynolds. And West
Atkins. Bliss.
Reynolds, Atkins,
Bliss.
and West Forsyth.
Yeah,
Okay.
Yeah.
Reynolds touches what?
Mount Tyler.
Mount Tabor,
Reagan.
Reagan,
Forsyth.
and West Forsyth.
Atkins.
Oh, yeah, we don't have them touching Atkins yet. Okay.
What exactly is this?
School districts.
Yeah, but what am I
Yeah,
missing?
hold on. Hold on, I'm getting there. So, Reagan touches what?
West Forsyth.
We got Mount Tabor and West Forsyth.
North side.
Okay. I don't think we missed any. I think we got them all.
Yeah, we got
See, I
a
was gonna draw that.
So, I should be able to give you this picture, and I should be able to say how many school zones border Carver. What would you tell me?
Wait.
5. 5 school zones border Carver.
It's none of these ones.
Sometimes the graphs that you draw to represent these situations, it's a little easier to count and see things. How many school zones does Reynolds touch?
Reynolds,
3.
4. No, 5. No, 4. I
6,
don't know, I
bro.
only see 4 on my paper, but it's hard to see on my paper.
It's 6.
There are 6 there.
I said Reynolds.
That is Reynolds.
That is Reynolds. There's 6 lines that touch the. Questions on graph models and how to draw them from situations. Okay. That leads us into our last section. So, what I want you to do right now, you've got 3 graphs at the top. I want you to try to take your pencil and start at the dots that I give you, and I want you to try to trace every line and make it back to that dot without lifting your pencil.
I know.
Take a couple
Do I have to
minutes
cover
and
every
try
line?
these. You have to cover every line and go back to that dot.
How am I gonna know, like, that I covered it? No, I'm all you.
Trace it with your pencil. You can't see pencil lines on your paper?
Not over black ink.
I don't know, when you cover it, instead of doing a straight line, do a squiggly line. Or there's highlighters over there, you're welcome to use a highlighter.
Can you go over it more than once or no?
Yeah,
Okay.
no,
No.
you cannot trace a line more than once.
Sure.
Okay, so your job is to put your pencil down, try to trace it all and get back to that dot
Me one, too.
without going across a line more than once.
Oh!
You all right?
No.
That's that old man over there.
Oh,
Got it.
Oh, I thought it happened.
Bro, how?
Figured it out. Is it okay if I get to the dot and then go back a little bit. No wait.
You just can't go over a line twice.
Like I went like this.
You did that, girl. Good job. I like that.
Who did it?
Brandon.
You gotta pass gas again.
You will have one that you will be able to make it back to the dot and cover every line. You should have one that you can cover every line, you just can't get back to your starting point. And there should be one that you just can't get to every line without crossing more than once.
Well, it's in order.
See if you can figure out which one is which.
Cross the bathroom.
No, you've already been there.
I ain't even used it. He called my name. We was talking real quick. That was, you heard the conversation. That was-
About that airline food.
Did you just say, how about that airline food?
Yeah.
What does airline food have to do with what we're doing?
I don't know.
Strange child.
I was hoping you knew that.
You're the one that's shouting airline food.
I mean,
It's alright, sure.
I mean, I don't know what's going through your head.
me either sometimes.
Apparently just airline food. Did anybody find the graph where you can start at the dot, cross every line and make it back?
Yes.
Which one? The middle one,
Yeah, that's the one I got. That's the one I did good on.
okay?
Yeah. Other than that, it's a wrap.
The middle one, you can start at your dot, you can touch every line and make it back.
But you can touch.
Won't.
Yeah, keep going. Keep going.
I just messed that up, didn't I?
No. Keep going. Keep going. Keep going. Now go down and then go stop in the middle and then get that square.
Aha. Okay. So this one is closed because you can make it back to the starting point with touching every line. Did anybody find the one that is neither, where you just can't cross every line?
The first one.
The last one.
The last
Yeah,
one.
because mine was the last one too.
Okay. So
Mine was the last one. I just said the first one to see like. I know how they go. I'm trying to get everybody else there.
Right, bro, I feel you.
Right.
yeah, there's just no possible way.
I just
You
traced all
get
of them.
stuck. Okay. No matter what you do, you get stuck. So this one is neither. Which means this first one should be open. Which means I can start here. I can touch every piece. I just can't go back to the beginning. Okay. So you started up there, but you ended down here. Okay. So if you had to look at all three of these, and I told you path and circuit, which one of these do you think represents a path? Which one of these do you think would represent a circuit?
Circuit is the closed.
Right.
Path
Your
is-
circuit is the closed, and your path is the open. What additional characteristics or requirements did we have to do unicursal tracing, which is what you just did? What did I tell you you couldn't do?
Retrace
So
over.
over the same
You
line
can't
twice.
retrace a line. Good. Can't retrace a line. Okay? You cannot retrace a line. Every line is used once. So that leads us into the rest of this chapter, where we're going to talk about Euler. Okay?
Who's that?
He is a mathematician that has created Euler paths and Euler circuits. So, a Euler path is a path that travels through every edge of the graph. You have to touch every edge once and only once. The thing is, a path has a different starting and ending point. A Euler circuit is one that travels through every edge of the graph once, but goes back to the same spot. So the biggest thing that you must remember with Euler is every edge once. Every edge once.
After this, got to know.
When I am fully done with notes. So your biggest thing in this, the rest of this chapter is going to be every edge once. Okay. We've got some theorems to talk about, and instead of me telling you them, you're going to figure them out for yourself. You heard me. So we're going to do this investigation. Okay. We said that we had a circuit if we could start at a dot, touch every line once, and make it back to that dot. So if you look at graph 1, do you think we have a circuit or a path?
Yeah.
Circuit. I mean, a path.
Oh, sorry.
Yeah, that's what I meant. Circuit.
This is a circuit. Okay. I can pick any one of these points and make it back. Okay, it's a big old square. Okay. Number 2 wants us to find the degree of each vertex of the graph. What is the degree of A? 2. There is 2 lines coming out of it. It's what?
2 for everybody.
It's 2 for everybody.
Yeah, every.
And the last thing they want us to find is what is the total amount of edges of the graph?
4.
Okay? Take a look at graph number 2.
It's path.
You say this one's a path. Okay? So if I start at A, I can trace down, around, and I end at C. So this would be my start and this would be my end. So yes, this is a path, not a circuit. You do not go back to the starting point. What is the degree of A?
3,
B,
2,
C,
3,
D,
2,
and how many total edges?
5.
5. Graph number 3. I think this is a circuit. Let's try it. 1, 2, 3, 4, 5, 6. Absolutely. We started and ended at A. So yes, this is a circuit. What is the degree of A?
4.
B,
4.
C,
2.
D.
2.
Total edges. 6 total edges. Graph number 4. Path. Okay. I can start at A and I end at B.
Yeah.
So this is a path. A has a degree of
1,
B,
3,
C,
2,
D.
2,
Total edges.
4.
And finally, graph number 5.
Circuit.
You think it's a circuit?
It is circuit.
2.
Oh, never mind that.
Yes, the path.
Can't start at A.
Yes, so I can see.
You said we can start at C?
Like, see.
Okay, so we started at C and ended at F. So this is a path. A has a degree of
2.
B,
2.
C,
3.
D,
2.
E,
2.
F.
3.
Fantastic. Total edges.
7.
Now, when you flip the page, we're going to make some observations. Okay, so we already said, what type of vertex can you start and end at for a Euler circuit? Well, we start and end at the same. Okay. Also, make note that this works from anywhere.
That's the same. Oh.
Okay. This works from anywhere. So that means I can start at vertex A. I can start at vertex G. I can start wherever I want when there's a circuit. So you start and end at the same vertex, and it works from anywhere. I'm going to come back to this page, but I want to look at this second question. What do all vertices have in common? So if we go back here, my circuits were this one and this one. What do you notice about the vertices?
They're all even numbers.
They're all even numbers. Okay, every time. So if you have a circuit, all vertices are even. If you have any odd vertices at all, it's automatically not a circuit.
Oh, that's what we look at.
That's one of the theorems. You just found that yourself. I didn't have to tell you that. Okay. What about a Euler path? What type of vertex can you start and end at?
Any two?
Okay. So that means that we start and end at different vertices. Okay. You start and end at different vertices. You can't go back to the beginning. All right. So let's go back at this. Take a look at all of your paths. Some vertices are odd. How many are odd in graph 2? 2 odd. How many are odd in graph 4? 2 odd. How many are odd in graph 5?
So they always got 2 odd.
A path will always have 2 odd vertices.
So that has more than 5.
It's neither. Okay. So it has 2 odd vertices. Exactly. 2 odd vertices. If you have anything else, then it is called neither. There is no circuit, nor is there a path. Okay. Also, take a look. Graph number 2. I said we started at A and ended at C. A is
3.
C is
3.
okay. Take a look here. We started at A and ended at B. 1 and 3. We started at C and ended at F. 3 and 3. So when you have a path, you must always start at one odd vertice and end at the other one. So that's also very important. So we start and end. We start and end at the odd vertices. You cannot draw a path if you start at the even one. It doesn't work. When you saw me do graph number 5 and I tried to start at A and you saw it go crazy, you cannot do it. That's when Andy said, no, you gotta start at C. You must start and end at your odd vertices. So, this is everything you just said. So, Euler's circuit theorem says, if a graph has any odd vertices, it cannot have a Euler circuit. That's what you just discovered. If there's any type of odd vertices, there is no Euler circuit. Also, if a graph is connected and every vertex is even, then you have at least one Euler circuit. You may have more than one. You could have 17, but you have at least one circuit if every vertex is even. Number 2 says, if a graph has more than 2 odd, okay, if you have more than 2 odd vertices, then it cannot have a path. Okay, it has to be exact, which is what part B says. If a connected graph has exactly 2 odd vertices, then it has a path.
Smooth.
Yes.
How much longer are you?
Maybe like 10 minutes. I mean, you're just going to miss part of the investigation if you want to. Is it going to take you long?
I'll try to read.
Huh?
I'll wait.
Any questions about the first 2 theorems? Okay. All even for a circuit, exactly 2 odd for a path. Your next investigation is going to give us 2 formulas. And then we're done.
Yeah.
Okay. 2 formulas and we're done. Okay. So we're kind of doing the same thing here, but all we're looking at is the degree of each vertex and the total number of edges in the graphs. So if you take a look at graph 6, what is the degree of A? A has 2. B has
2.
C has
3.
D has
3.
3. E has
2.
F has
2.
G has. What's the total lines? Total edges?
8.
8. And what did you say, Mr. Burleson?
10.
No, because it was right. It's a path. Okay, this one's a path. C and D are the only 2 odds. Take a look at graph 7, and yes, I know it looks crazy. There's a lot of lines here. A has how many?
5.
5. B has 5. C has
5.
5. D has
3.
E
8.
8 and F
4.
4. If you had to classify this one,
Neither.
okay, it's neither. There is more than 2 odd. How many total edges are here?
15.
Huh?
15.
15. Fantastic. Okay, finally, graph 8. A has a degree of
3.
3. B,
3.
C,
3.
D.
3.
Total edges.
4. 6.
6. Remember, your loop only counts as 2 when we're talking about degrees. It's still only 1 edge. Okay, before we skip to the next little piece here, if I added up all of my degrees for graph 6, 7, and 8, what's the total amount of degrees in graph 6?
15. 16.
16.
No.
It should be 16.
No.
Okay. What
So
about
are you going to tell me
7?
that the total edges is always half of the...
Yes. All right, so he's already gotten it. 16 and 8. 8 is half of 16. So if I have 15 edges, what, there should be 30, and this should be 12. Fantastic. So, this leads us to observation number 2, which says the number of edges equals the total degree divided by 2. Okay. Your number of edges is half the amount of your total degree. Or I can write this the other way. Your total degree equals 2 times your number of edges. Okay? Your total degree is twice your number of edges. So again, instead of me giving you formulas, you just came up with them on your own. This is what mathematicians do.
What they do?
They come up with this stuff on their own.
Whoa.
So I now give you all mathematicians.
For real?
I'm the worst at it.
Okay? The next piece says, is this relationship also true in graphs 1 through 5 that we already did?
Yeah.
If we back up, what was my total degree here? 8. We had 4 edges.
Yeah.
Works. Here we've got 6,
It's
10.
Oh, yeah,
5.
you do.
Here we've got
12.
12 and 6. Here we have 8 and 4. So the answer to that question is yes.
Yeah, we do. Oh, yeah, we do.
Okay.
Okay. Oh, yeah, we do.
So that leads us to our end.
Whoa.
So my last theorem, Euler's sum of degrees theorem, says the sum of the degrees of all vertices of a graph equals twice the number of edges. Okay. Those formulas you just wrote down, this is that in words. It also says a graph always has to have an even number of odd vertices. Okay, so that means you'll never have a graph with 1 odd vertice, or 3 odd vertices, or 5 odd vertices. There's always an even number. You cannot draw a graph that has an odd number of odd vertices. So, to sum everything up in a nice little chart here, if I have no odd vertices, what do I have? Circuit. If I have exactly 2 odd,
That's a pass.
I have a path. If I have an even number of odd vertices, so 4 odd or 6 odd or 10 odd, what would my answer be? Neither. And your last one, if I have 1 odd or 3 odd or 5 odd, you should never ever see a graph like this. No, this is impossible. You cannot do it. That's what this theorem just said. Okay. A graph always has to have an even number of odd vertices. So to have an odd number of them is impossible. Any questions?
I know, we know.
So
I have a question.
Yes.
How do